Okay, so this is going to be a talk about Jepson and specifically about Elle, which is about database safety verification. My name is Kyle Kingsbury. You might know me as Afer from the internet. Pronouns are he, him. And my day job, as Karen mentioned, is to break databases. So I test distributed systems and then I write about them. Before I did that, I was a backend engineer and I worked on public-facing APIs at a few web startups. APIs aren't physical things. You can't like pick up an API and hand it to somebody. They're illusions, like rainbows. People look at them, but they can't touch them. And like all rainbows, these APIs are supported by some sort of girder, some infrastructure, a code that we wrote in some programming language, which lives on top of this runtime, which I've represented here by these wooden pilings. And that runtime is in turn planted on top of this firm foundations of distributed databases and persistent systems that we found lying around on SourceForge in 2009. Now, as anybody who's ever run a database knows, the pile of tires is usually on fire. And it's our job as engineers to engage in what we call information hiding, to build the tower of abstraction higher and higher away from the flames, so that even though our engineers are fighting to put more tires onto the fire and pull the burning ones off and roll them into the sea, people who are using the API don't notice. We want to build reliable systems out of unreliable parts. But how reliable are those systems really? I think the only way to really find out is for us to measure. So I've been working on ways to measure distributed systems and see what they actually do. The work I've been proceeding with for the last, 8 years now is called Jepson. And it's a library and sort of workbench for plugging in arbitrary distributed systems and doing testing on almost any sort of concurrent system. In Jepson, our environment are things like clients and Jepson itself. It pretends to be a bunch of concurrent users or programs that are interacting with some distributed system. The system is going to be typically a database or a queue, some Linux processes that communicate via an IP network running on Linux machines in a data center. At the boundary between clients and servers, there should be some laws that hold. So for example, if I'm testing a queue, I might want to make sure that everything I put into the queue eventually comes out again. If I'm trying to test my house, maybe I have one dog, and if I open the back door and I wait for a while and I see one dog go out and then I see another dog go out, I know that something's gone wrong. Either, I had a surprise dog in my house, or the dog is teleporting back inside the home somehow, or my front door is open. Just by watching the boundary between the inside and outside of the system, I should be able to intuit some laws. So we're going to run a bunch of simulated clients outside the database. They're going to interact with it via the network, and hopefully it will look like one coherent thing. Now, we do no instrumentation in Jepson. There's no static analysis, no injection of probes or tracing. We're just running an arbitrary binary. Anything that you can talk to over the network is fair game. All that we get to see is what the clients know. So the question is then, can we reconstruct what happened inside the database purely from observable outside phenomena? To give you a concrete example, I might generate a write operation, like set the key X to 5, submit it to the server, and I get back a response. And I need to classify that response in one of basically 3 ways. One is that the response is successful, and I know the operation took place. Another is that it failed, and I know it didn't take place. Or something else could happen. I could get some sort of indeterminate response, a crash, a timeout, who knows. I'm going to have to leave that invocation open for the rest of the test because it could take place at any time after invocation. So what I get from this pattern of interaction is sort of a tapestry of logical operations and their concurrency structure. And then given this data structure, this history, I could start to ask questions like, can I find a path through the history that looks like I expect a database to behave? Could I execute all the transactions in total order? That would be serializability. I want to take an arbitrary collection of invocations and completions and say, is this history serializable? Is it equivalent to some total order? Now, at first glance, you say, well, we've got SAT solvers. Why don't we encode the transactions as if they had ordering dependencies, having to see previous effects and the modifying state? We'll plug that whole thing into a constraint solver, a SAT solver, turn the crank, and out should come a solution. And if it says unsatisfiable, then we know it's not serializable. And this approach works, but it's not ideal. For one, it's exponential because there are many possible combinations for orders. And for another, when it says that the solution is not satisfiable, it doesn't tell us anything about why. So you're staring at this 60,000 element history that you recorded over 10 hours, and you have no idea where the database actually went wrong. That's not really great from a debugger perspective. So what we want to be able to do is localize a fault to a specific subset of transactions, and ideally be able to explain why it was an anomaly. To do that, we're going to adapt work from Atul Aja. His formalism for consistency models is sort of a lingua franca in the database community. And Aja says that we can build a dependency graph between transactions. So the nodes in this graph are individual transactions, and the dependency edges are things like a write-read dependency, when T1 writes something and then transaction 2 observes that value. Or transaction 1 could write something and T2 could overwrite that value. That would also tell us T2 executes second. Or transaction 2 could overwrite something that T1 read. And if we have these three types of relationships, then we could build a dependency graph between transactions. And if it were serializable, then there shouldn't exist any cycles in this graph. I should be able to topologically sort it and just construct an order. But if I can find a cycle, well, then I have an example, a counterexample really, to a consistency model. I can say, these two transactions can't have executed in any order. But this isn't as easy as it seems, because if I am interacting with the database as a client, I don't actually have access to individual versions. What I have are values. So when I set key X to 2, and another transaction sets key X to 2, and a third transaction reads X2, which one of those 2s did it read? I can't tell. They're indistinguishable from the database's perspective. And worse, that formalism assumes that there is a total order of versions for every key. So if I have transaction 1 set X to 1 and transaction 2 set X to 2, which one executes first? Well, I don't know. I have no way to reconstruct the dependency order here. Now, in Aja's formalism, this is given. Like every history just has a total order of versions. And you can imagine we could plug this into the SAT solver and say, can you find a version order for me? But again, that would require an exponential search. So it would seem like we're stuck. Here's the trick. We redefine our database in terms of a different data type and a different type of operation. Instead of overwriting registers, we're going to use lists. And our writes are going to append a uniquely chosen value to the end of the list. So if we have list 1, 3, and we append 2 to that list, we get the list 1, 3, 2. This gives us two important properties. One of them is what I'll call recoverability. And that's if transaction 1 appends X2, anybody that reads X and sees a value ending in 2 must have observed the value that resulted specifically from that append operation. Because every single write changes the end of the list, and all those changes are unique. So I can map between reads and writes. The other thing we get is called traceability. And this is any single read of a value. Like if I see X's value is 3, 2, I know that X must have initially been the empty list, then the list 3, then the list 3, 2, and so on. So I can reconstruct a prefix of the version order from any single read. So that's cool. Maybe I don't get the whole version order, but as long as I read periodically, I'm going to get hopefully 90% of it or more. What we're doing here is we're inferring a subgraph of any true Aja history that must have existed in the database, had the database actually had one. Now, databases don't operate in terms of Aja's formalism. They're using locks or multi-version concurrency control. They don't necessarily have this graph internally. But if they did, then we can reconstruct a subgraph of what it must have been. And we might not observe all of the edges. So for example, here, the database might have an edge between transaction 1 and transaction 3, which we don't get to infer because we never saw those values read, perhaps. But the fact that it's a subgraph tells us that any anomalies, any cycles we infer in this inferred graph, they must also be present in the actual database itself, assuming it had an object history. Programming language people would say that this is a sound but not complete checker. We might fail to observe some anomalies, but any anomaly we do observe is hopefully a real one. So using this technique, we can write a single workload which generates random transactions with relatively few constraints. We can mix reads and writes freely. We can generate any number of operations or any number of keys. And from that, we can get write cycles, aborted and intermediate reads, cyclic information flow, read skew, anti-dependency cycles, the whole family of object anomalies, except for predicates. I haven't figured out what to do about those yet. And in addition, we can get anomalies that aren't present in object formalism. So like, if you read a value that nobody ever wrote at all, we call that a garbage read. This happens sometimes when the database has like memory corruption or some sort of like wire gets crossed internally. We can find incompatible versions of a single record. So if I see two different versions of a list, neither one of which is a prefix of the other, then I know that there had to be some kind of split brain. They can't have come from the same unitary single-threaded history. I can find internal consistency violations inside the scope of a single transaction by making sure that every append appears at the end of the list in the next read. And I can identify duplicate writes because every write is unique. To give you an example, imagine I execute these three transactions. First, I append 1 to key X, and then I append 2 to X and 2 to Y. And then I ask for the values of X and Y, and the database tells me X is currently 2, 1, and Y is currently empty list. It's not immediately obvious if this is serializable or not, so let's do a little bit of inference. Looking at the read of X2, 1, that tells me the append of X2 had to happen before the append of X1. So I've used the version order inference and traceability to map the write-write dependency. The fact that I read a value that ended in 1, that must have come from the append of X1, because appends always go to the end of the list. That gives me a write-read edge. And the fact that I observed the empty value of Y and failed to observe the append of Y2, that gives me a read-write anti-dependency. So I have a cycle here, including exactly one read-write edge, that's G single. This is a violation of both repeatable read and snapshot isolation. And from that, I can also rule out serializability and strict serializability. So I run this one workload, and Elle will actually spit out counterexamples. It will draw graphs between transactions. It will explain in plain text what the dependencies are between them and why it's a violation. And it will also rule out some set of consistency models, all automatically. And instead of taking exponential time, this inference is linear, thanks to the fact that Tarjan gives us a linear time algorithm for finding strongly connected components. Waving my hands a little bit, we do a breadth first search inside each cycle, but once we've gotten a cycle, we can prove at least it's not serializable. Is it fast? Yes. Where previous checkers I've worked on, for example, Gnosis for linearizability checking, they have an exponential blowup. And after more than 40 concurrent processes, they basically are untractable over a few thousand transactions. Elle will handle hundreds of thousands of transactions, and its growth is linear in time. It's also essentially insensitive to concurrency. And this is really important because in a real-world test, transactions and requests crash all the time, which drives concurrency through the roof. So this gives us really nice properties. To back up, we're going to generate randomized transactions. We're going to apply them to the database using a client and record a history of their execution. We're going to plug that history into Elle, and it's going to spit out anomalies and tell us what kinds of isolation levels it thinks are ruled out. And while this is going on, we're going to inject network partitions and process crashes and all kinds of different faults to make sure that we're getting a good test of distributed behavior. So I'd like to talk about 3 databases and what we found using Elle. The first of them is Postgres version 12.3. This is work from last June. Postgres is a single node SQL database. This is not a distributed systems test. We're only talking to a single machine. Postgres serializability is actually serializable snapshot isolation. It's a tad stronger than serializable. Its repeatable read actually means snapshot isolation, and the default is read committed. There is no read uncommitted level in Postgres. If you ask for it, you get read committed by default. Now, the fact that Postgres repeatable read is actually snapshot isolation is a little odd, because if you're familiar with Adja and Berenson's like map of consistency diagrams, map of consistency models, you know, these aren't actually directly comparable. So is there a difference? Can we observe it? Let's try it out. Let's spit a bunch of transactions at Postgres at repeatable read and see what comes out. What we get are histories like the following. The top transaction reads the value of y as ending in 2, and it does not observe this append of 4 to key y. The middle transaction appends 5 to y, which is visible to the bottom transaction. And the bottom transaction fails to observe the top transaction's append of 8. So we have a cycle here, including 2 adjacent read-write edges. It's only on individual keys, not predicates. So this is G2 item. This is a violation of repeatable read in Adja's formalism. But it's legal under snapshot isolation. So this is a sort of strange question. Like, Postgres says the repeatable read is stronger than the SQL standard repeatable read. Is it? It kind of depends. The SQL standard, as Berenson and Adja point out in detail, is ambiguous. It allows multiple interpretations, some of which have anomalies that the other interpretations don't. Berenson and Adja would argue that the spec is essentially bad and that we need to be using a broader interpretation of the prohibited anomalies. But that's not what Postgres did, and to some extent that's defensible because the language is ambiguous. Okay, enough hair splitting. Let's do an actual serializability test. The way that serializability works in Postgres is by preventing dangerous structures, which are cycles of dependencies that include multiple adjacent read-write edges. They give a couple of examples in the paper. What we actually observe at Postgres serializable are histories like this. The top transaction reads the empty value of x, which means it had to execute before the bottom transaction appended something to x. And the bottom transaction saw the empty value of y, which means it had to execute before the top transaction added something to y. This is an example of long fork. It's also G2 item. We have more complex examples too. There can be write read edges in there. This is another G2 item example. And if you kind of zoom out of these and you just draw circles around the transactions, what you notice is that these are exactly the same transaction structures that are supposed to be prohibited under Postgres serializability. So that's kind of cool. Where Postgres claimed to be serializable snapshot isolation, in fact, was not even a repeatable read. The best consistency model that it could have been was strong snapshot isolation, which is snapshot isolation plus real-time edges. I should note, we're not limited just to doing data dependencies. We can also use the real-time and the per session dependencies between transactions to verify properties like strict serializable versus serializable. So this happened because the conflict detection mechanism in Postgres would tag a single transaction as the owner of both the old and new versions of a tuple. And then the transaction could commit and the conflict checker would say, oh, these are both in the same transaction. There's no conflict here. I don't need to abort it. This is fixed in basically every version that was released last summer. So if you care about serializable Postgres, please do go ahead and make sure you're running one of these versions. Best guess for serializable current behavior is that it is in fact strict serializable on a single node. Repeatable read is strong snapshot isolation, and read committed does appear to be read committed. Next, MongoDB. This is version 4.2.6, also research from last June. MongoDB claimed to offer among the strongest data consistency, correctness, and safety guarantees of any database available today, including, quote, full ACID transactions. Now, when you hear full ACID, you're probably thinking about isolated transactions that don't interleave with each other, i.e. something like serializability or maybe strict serializability. But what Mongo's claims actually were snapshot isolation, which is maybe a little bit lower. But that assumes that you use majority writes and snapshot reads. The defaults in Mongo are that committed writes can be thrown away silently at basically any time, and that reads give you whatever a local node happens to think is the value without checking with anybody else to see if it's even committed. So the default behavior for Mongo is not in fact serializable. It's read uncommitted, maybe even weaker, I'm not quite sure. So let's give this a shot. Let's take a workload that we know is safe. We'll create a collection handle. We ask the database to give us read concern linearizable, write concern majority, and we'll do some compare and sets to append values to the end of a single document. And this is in fact snapshot isolated. It's also linearizable. Everything looks great. Now we'll add a transaction to the exact same code. Still linearizable, still at majority. We're just going to wrap that single operation in a transaction. And suddenly it loses writes and exhibits aborted reads. That's a little bit problematic. As it turned out, transactions in the client would silently downgrade your requested read concern to local and ignore higher levels of safety that you had previously requested for the collection. So you need to always say with read concern snapshot on every transaction. But if you do that, you still actually get split brain aborted reads. It's not snapshot isolated. And that's because snapshot reads don't actually do snapshots unless you also use write concern majority. And you'd ask, well, hang on a second. If I'm doing a read-only transaction, do I need to use write concern majority? After all, I'm just looking at things, not changing them. And if you try it, you observe behavior like this. I read key X a whole bunch of times. X is empty, 1, 5, 1, 5, 6. Then all those values vanish and are replaced by 3 and 3, 7, as if 1, 5, 6 had never been written at all. This is very much not snapshot isolated. So every single transaction, you have to use read concern snapshot and write concern majority, even if all you're doing is a read. This is all documented. It's just really surprising for anybody who's used a database before. Now, do Mongo's users know to do this? I'm not necessarily sure. Mongo's own research from PLDB 2019 suggests that 80% of users use the default read concern and 99.6% use the default, 80% use the default write concern, 99.6% use the default read concern. Now, does that mean that they want to and understand those properties, or did they just kind of accidentally wind up doing it? Not really sure. Mongo's own documentation examples didn't do snapshot isolation. They used read concern local with write-only transactions, or they just used the defaults, which are unsafe. I looked around at a whole bunch of third-party blog posts to see if like the community in general understood what to do, and they didn't. They all were claiming to use snapshot isolated or ACID transactions, but they were inadvertently, or maybe intentionally, choosing to allow write loss and aborted reads. So I think there's a little bit of an educational problem here. If you're going to choose these weird default behaviors, you need to have an aggressive education campaign to balance that. Now, is snapshot isolation actually ACID? Maybe. Like here's a pair of transactions we recorded from Mongo using those strongest properties. This is an example of long fork. The top transaction sees Y as empty, fails to observe the bottom transaction's append of Y. Bottom transactions is X empty, fails to observe the top transaction's append. So these transactions, both fail to see the other. This is G2 item, right skew. It's legal under snapshot isolation, but it's not isolated. So this leads to this kind of weird thing where like full ACID transactions allows you to get these giant clusters of transactions, all of which depend on every other one and can't have executed in any total order. What does full ACID mean if this is legal? I'm not sure. In a lot of our tests, it was easy to get like 10% of transactions that were involved in isolation violations of some kind. Does that matter? Probably not, I hope. It would depend on the concurrency of the workload. We're intentionally targeting the same keys for lots of transactions at a time in Jepson. And it's not necessarily the case that just because something has an anomaly that it results in a logical application violation. As far as I know, that's kind of an open research problem. But it's maybe worth keeping in mind when you're trying to use MongoDB. So are those majority snapshot transactions actually snapshot isolated? As you can probably guess, the answer is no. You could append a key, you could append 6 to X, and then 6 would show up multiple times in the record. You might think, oh, maybe this is like a transaction retry mechanism. And so you try to turn off the retry mechanism, but you can't because the client disables it as soon as you turn on transactions. So you wind up with these weird histories where the top transaction here adds 4 to Y, and then the middle transaction is 5 to Y, and a read of Y shows 4 or 5, so we know they happen in order. Middle transactions use x1, 2, fails to observe the bottom transaction. Bottom transaction is in turn visible to top transaction. This is a violation of snapshot isolation. This is a read skew. So we're not supposed to see this, but even worse, we have transactions which both observe each other's effects. Like here, the top transaction's append of 3 to key y is visible to the bottom transaction, and the bottom transaction append of x5 is visible to the top transaction. That's really bad. This is cyclic information flow. But worse yet, we can have cases where a single transaction executes a read and observes its own effects from the future. So here, the append of x1, I executed later, and somehow that write time traveled backwards to appear in my own read. So yeah, there's also 3 other transactions that got like squeezed into this one. This is an internal consistency violation. It's definitely not supposed to happen in a snapshot isolated database. So while MongoDB claimed to offer snapshot isolation, its strongest isolation level was in fact weaker than read uncommitted. Okay, so this is due to bug server 48307. Committed transactions would incorrectly appear to fail. They would get retried internally, and then the retry could observe the previous effects of that transaction. That was fixed in version 428. I did some really cursory testing, like 5 minutes, and it looked like it was snapshot isolated, but I haven't dug into it in depth. Do keep in mind that the defaults, at least last I checked, were still read uncommitted or weaker. So, think about that when you're designing your application. Last but not least, I'd like to talk about CillaDB, version 4.2 RC3. Cilla is basically Cassandra, but hopefully faster. It's a wide column store. So instead of having a sort of rigorous grid of rows and columns, each row could have a variable number of columns. It uses an eventually consistent data model by default with last write wins, and it has an optional Paxos-based transaction system. Now, last write wins means that every cell, every unit of data in Cilla is basically a triple of a key, a value, and a timestamp. And if you're going to have 2 different versions of a cell, you're always going to pick the one that has the highest timestamp, or the lexicographically highest version to break ties. So here, the dog that's sleepy takes precedence over the dog that's playful because it was written with a higher timestamp. These timestamps are derived from the local clocks on individual nodes. This results in some kind of strange behaviors that aren't immediately intuitive. For instance, if I wanted to add to a number, and I had one client add 1 and one client add 2, here the client on the left gets timestamp 8 and writes 1 with timestamp 8. Client on the right adds 2 and writes it with timestamp 7. Timestamp 8 is bigger, so 1 wins. And somehow 0 plus 1 plus 2 is equal to 1. You could imagine that the timestamps could be reversed, but that actually wouldn't make it any better because it would then be 0 plus 1 plus 2 equals 2. Either way, we've lost a write. So this is a classic problem in last write wins. It allows lost update. There is no safe way to update data in Cilla or Cassandra's data model using the eventually consistent mechanism, as long as you're trying to write something that depends on a read. If you want to do that, you should use lightweight transactions. And that's where you go through Paxos. There's 3 round trips in Cilla, a little bit faster than Cassandra, which is 4 round trips. A little bit slower than Raft, which uses 1 round trip, as long as there's a stable leader. But if you do this, you should get linearizable transactions. Those transactions are of 2 forms. You can do a select statement, and you can select multiple keys sometimes, only if none of the columns you're reading are structures like maps or sets or lists. The other type of transaction you can do is basically a batch update. So you start a batch, you do a bunch of updates, inserts, deletes, and then you can commit that atomically. You can't mix reads and writes together. The other constraint is that all these operations have to be in the same partition. So this is a really narrow view of what a transaction is, but it should hopefully still be linearizable. Except with lightweight transactions, we found instances of aborted read. During conditions of process crashes and network partitions, you could append a value and get back a result like unavailable exception, not enough replicas available for query. And that to me sounds like it didn't do the right, like it's a definite failure. And the documentation suggests this is actually definitely a failure. But it's not. Sometimes that right actually succeeds and you get to see it later. So in Scilla 4 through RC1, they changed this exception to a write timeout exception, which suggests to users, oh, this might have happened, might not have happened. Cool, problem solved. We found issues with non-lightweight transaction isolation as well. The Scilla docs say that when you're doing plain old insert, update, delete, and batch, it's, quote, isolated and atomic. And again, when you're talking about isolated atomic transactions, you're thinking about something like serializability, typically, where transactions appear to take place as if they were instantaneous, executed in some total order. But this can't possibly be the case for Scylla's data model, because Scilla allows us to do updates on individual replicas without them communicating. CAP rules out serializability for this. Imagine I added 2 to the empty set on the left replica and 1 to the empty set on the right replica. I could read the set 2 on one and read the set 1 on the other. Well, these 2 sets can't possibly have come from any total order of adding these together. I should have seen either the set 2 and then 1, 2, or the set 1 and then 1, 2. So I know that if I'm using CQL collections that I can't be serializable, not without going to lightweight transactions. But this isn't just a problem with CQL. In fact, individual writes to rows can also violate isolation. So to test this, imagine that I do a bunch of batch writes where I update 2 different keys in the same row each time. And so I can tell if they came from the same transaction. I'm always going to set them to plus or minus the same value, like X is 1, Y is -1, or X and Y are both 2, or they're both -3. The thing that this gives me is if I read X and Y together, I should be able to observe that they're all plus or minus the same value. And that's true most of the time. But sometimes I get a mixed state. Like here, +7 and -3, they must have come from different transactions. They can't possibly have executed from any isolated series of writes. And this happens even with consistency level all, which is where every single replica has to unanimously participate in the write, even with the atomic monotonic timestamp generator, even with no cluster faults, totally healthy machines, and perfectly synchronized clocks. In fact, the better synchronized your clocks, the worse this problem is. Under healthy conditions on local machines, 500 reads, 500 writes per second, we saw isolation violations roughly every 20 seconds. How does this happen? Well, conflict resolution in Scilla and in Cassandra proceeds on a cell-by-cell basis, not on a row-by-row or write-by-write basis. So if one client writes X is 1 and Y is -1, and it uses timestamp 5, and another client writes X is -2 and Y is 2, also at timestamp 5, then Scilla is going to merge key X, and it has 2 different values. It's got a 1 and a -2, same timestamp. So it picks the lexicographically higher one and gets 1. Then it looks at -1 and +2 and says, oh, same timestamp, which one's bigger? 2. And it results in a mixed state. Now we have read skew. So this isn't news. I mean, I reported this in Cassandra in 2013. Cassandra's own engineers reported it could also happen with read repair in 2014. Scylla's engineers reported it in 2017, and there are still, at least as of December, still open issues in Cassandra about fixing this. And yet the Cassandra doc still said writes are performed with full row level isolation, as if that were a meaningful sentence that people had understood. So the Scilla docs were copied from the Cassandra docs, and as a result of our collaboration, they no longer make this incorrect isolation claim, and now instead they give you examples of what happens when transactions conflict. So I'm hoping that this will help guide users not to assume that they can write multiple things together. For instance, it would not be safe to write a user's password and like salt as 2 different fields together, because if they were to do 2 updates concurrently, they could end up with a password and salt that didn't match each other. Another bug we found involved lightweight transactions and stale reads. you could write a value and it would be visible to reads. And then 40 seconds would elapse and the value would suddenly flip back to something that it was 40 seconds ago. That's definitely a violation of real-time linearizability. And this happened even in healthy clusters and just with single reads and writes, no transactions involved. In fact, out of one of our tests, out of 1,100 transactions, 260 of them were involved in one single isolation violation. But at least it's just seeing past states. It's not like we actually corrupted data, right? Sometimes. Sometimes we got values where a prefix of the list and a postfix of the list would disappear. So like here, the list suddenly shrinks to be just 22, 23, 24, and then the values before and after pop back into existence again. Definitely not something you expect from a linearizable system. Or we could see a postfix of the list flicker back and forth between two different histories. So here, one set of nodes thinks that it's 2614, another set of nodes thinks it's 212, 212, and then at some later time, they just get like stitched together on top of each other. So again, linearizability assumes that there is a total order consistent with real-time order. This is not linearizable. And this happened even in healthy clusters, even with serial reads and lightweight transactional writes at the strongest possible isolation levels. This is due to an improper hashcode calculation. So when Scylla tries to compare two different versions of a row, it goes to both nodes and says, could you please checksum this row for me? And the hash calculation would stop whenever it saw a null value for some key. So if there were any differences in lexicographically bigger keys, Scylla wouldn't notice they had changed. And this is one of those things that you don't notice unless you happen to be generating random keys and random values. If you write your transactions by hand, you might not trigger this condition. So this is another advantage of randomized testing. That was fixed in version 4.2. We found a bunch of issues around membership changes. And these, again, could manifest as split brain. So you could see values switching back and forth between two completely independent histories that have nothing to do with each other. This was due to a bug in the way that repair happened. When you had a node that was streaming information from another, it didn't have to talk to a majority of the cluster. It only had to talk to a single node. So a repairing node could fail to observe writes that were happening on a majority component of the cluster. But it still counted for quorum reads. That was fixed in 8.2.9 B4C1, almost certainly released by now. We also found issues with list operations that chose the keys at the storage layer based on the node's local clock rather than timestamps, and that could lead to inconsistent ordering. And then we also found issues with membership changes that were performed concurrently. So in our testing, sometimes we'd issue a remove node command and it would get stuck. And then a couple minutes later, we'd issue like an add node command. And in most distributed systems, this is like kind of a normal operational process. Like you will occasionally have concurrent changes to cluster state, but you're not supposed to do that in Scylla, as I found out. You're supposed to wait and make sure that every previous membership operation is done before you start a new one. How do you do this? I have no idea. The tooling doesn't tell you when a membership change is complete. You just have to know. Maybe by like logging into every machine and making sure they all agree somehow. I'm not sure what you did during network partition. So what we did was we followed the documented process. We would ask a node, hey, do you think node C is down? And if there's a partition, A would say, yeah, C is inaccessible. Cool, go ahead and remove C. And C is in fact not actually dead. That could lead to improper quorums for the Paxos system. So what you have to do, according to Scylla, is you need to actually like log into the machine and kill or shut down that node to make sure it's really dead before you issue a remove command. If you can't reach it, you can't remove it. Was this documented? Absolutely not. You just had to know. So now there's documentation and users should know about this kind of operational property. As of December 2020, we found 7 issues in Scylla. 5 of them were already patched or documented. 2 are pending. Mostly stuff around documentation and then a rewrite of the membership system that was going to use Raft to coordinate cluster membership. I should also mention again that Timestamps and last write when systems are tricky and a constant source of surprises. So if you need order, you probably want to use lightweight transactions. To recap, when you choose a database, regardless of whether you're buying a commercial product or an open source one, you're essentially signing a contract. You're locking yourself into using the system for a while. You're going to write infrastructure. You're going to build operational expertise. That means that you really need to read the documentation carefully. And like Ariel, talking to Ursula the Sea Witch, you need to look out for the fine print. There might be secret rules, like you have to kiss the prince by the third day or all of your data is forfeit. You're never supposed to have a network partition. You're never supposed to remove nodes concurrently and adding them. So read the docs really carefully and look for these things. And then test it for yourself, because a lot of times behavior is undocumented or it's documented incorrectly. Look out for words like strict consistency, strong, acid. These are weasel words, which vendors use to tell you that a product is lovely and wonderful, but they don't necessarily mean what you might think. Acid can mean anything in vendor speak, from strict serializable to read uncommitted. I want to encourage both vendors and users to be formal and specific in the safety models they expect and they require. And that doesn't mean we all have to be serializable all the time. There are lots and lots of systems which are okay with eventually consistent data, that are okay even losing some records, as long as it's not too many. But when we do need safety, we should be able to say exactly what it is and hopefully get it. I always tell vendors to use proven algorithms. For a long time, there was an industry movement to make your own consensus system and write your own replication. And this resulted in nothing but pain. Nowadays, I think the industry has largely gotten the message. People are using Raft, they're using Paxos. These are, if not well-established in the case of Raft, still less than a decade old, but there are proofs, there's a lot of research around it. We think these things are safe-ish. But that's not enough. As it turns out, even if you're basing your work on Paxos, which has been around and proven for decades, you can still make mistakes in hashcode calculations, which make your guarantees invalid. So we need to do testing in addition to formal proofs. When we do that testing, we have to think about failure modes. And that means things like process crashes. If you run your tests and just kill nodes occasionally, you can get a lot of interesting behaviors. You can cause node failure by killing VMs or turning off the power. You can get clock skew with the date command or lib fake time. This doesn't have to be fancy to get results. You can simulate garbage collection IO pauses with sig stop and sig continue, which schedule and deschedule the process. And you can also get network partitions with IP tables or traffic control. And I think this is our best tool in finding bugs, because network partitions create long-lasting windows of concurrency that are big enough for our tools to observe anomalies in. We want to try and push those bounds long enough that A, we get phase changes in the system, and B, the anomalies are actually visible. It's not enough for us to test individual components. Ultimately, the composition of systems is sort of an underappreciated challenge. And so I want to encourage people when they're testing, not just to say, oh, like it's Jepson tested, this thing is safe, but like run your own tests on whatever services you built atop the database. And when you do this, use techniques from property-based testing. That means generating randomized inputs instead of a fixed schedule. Postgres had a really comprehensive test suite for their isolation violation system, for their isolation enforcement system, but it didn't find these anomalies. It took randomized inputs to get that. Verify your properties using high-level invariants. In the case of Elle, we can do automatic inference for all kinds of isolation anomalies, but it doesn't have to be fancy. It's okay for you to verify simple properties like users can only register a username once. That's something that most people can write a test for. When you're doing this testing, do it with distributed systems failure modes, not just in a healthy case. A lot of clusters only test things when they're fine, and as a result, they miss a lot of interesting behavior. Finally, running databases is hard, and this litany of failures that I've described, I wouldn't look down on anybody for having these problems. Like, none of these systems are perfect. They're trying to solve hard challenges and they're doing the best they can. So let's have a little bit of humility and respect for the people who are trying so hard to make databases work. This research would not have been possible without my wonderful collaborators, Peter Alvaro and Kit Patella. Peter's over at UC Santa Cruz, Kit's independent. Andres, Peter, Felix, Thomas, and Daniel from the Postgres team were really helpful in understanding Postgres behavior. Maxime Vignier inspired MongoDB work. CillaDB funded their research, and I was really helped by their engineers, including Camille, Peter, Fyodor, Dor, Duarte, Konstantin, Alejo, and Pavel. Thank you all very much for coming to this talk. I appreciate you so much, and I would love to have any questions.